Hello, good people out there in discrete math world. So this is the famous Pascal triangle, and we mentioned already that this is equal to the combinations, combinatorics, meaning that two choose one is two, three choose two is three, one choose zero is one, and so forth. Notice that I have it this way and I have it that way. It's sort of reverse of each other, but the reverse is true because that's the symmetry. And now that symmetry is easy to bear out from the formula because n choose k, well, by definition, is n factorial over n minus k factorial times k factorial. So, but applying the same definition, I get n choose n minus k is n factorial over n minus k, all that factorial, over n minus k factorial. I'm just applying the same formula, substituting n minus k for k, and this gives me n factorial, after I simplify it, k factorial, n minus k factorial, which is the same thing as this. So we see that this is the same as that, but it also makes sense, like if I have 10 people and I want to pick out 3 for a committee, so picking out 3 is the same thing as leaving out 7. You see what I'm saying? So the number of ways I could pick a 3-man committee is the same number of ways that I could leave out 7 people from the committee. So picking groups of 3 essentially is the same as picking groups of 7. And that's kind of a common sense understanding of the or an intuitive understanding of the symmetry of the combinations. Now I want to go to something else called the binomial theorem that's very famous and is connected to all this. The binomial theorem is basically telling us the coefficients of a binomial. So it's going to be n choose n minus 1, n choose n minus 2. The powers of a go down, the powers of b start going up, so you get to b to the n, and so forth. And these numbers here, n choose n minus 1, that's the same. That winds up being the same thing as the rows of of Pascal's triangle. So if I'm raising something to the 17th power, these coefficients would be the same as the 17th row of Pascal's triangle. But I want to understand, get again, some bit of understanding, what does this have to do with choosing? We're going to prove by induction that the binomial theorem works. But before we even get to that, why does it make sense? And what's it have to do with choosing things? So here's my little insight that I want to share with you. So I want us to start with a very simple case. I'm going to do x plus 1 to the 5th power. I'm just going to do the 5th power, not the nth power. Instead of b, I'll just make it 1, just make things simple. So x plus 1 to the 5th power, well, it's x plus 1 times x plus 1 times x plus 1. Now this is going to have, when I multiply this all out, I'm going to get a certain amount of x to the 5th, so I'm going to get a certain amount of x to the 4th, a certain amount of x to the 3rds, and so forth. Well, how many x to the 5ths are going to be? Well, I have to choose, there are 5 x's here. I would have to choose all, when I make my choice, I'd have to choose. See, I could always choose either an x or a 1. I always have a choice, x or 1, x or 1. So I would have to choose all 5 out of the 5 x's. So the number of ways I can get x to the 5th is just 5 choose 5, which is just one way. And how many ways can I have 4 x's? Well, I could choose these 4, or I could choose those 4, or I could choose these 4. Well, it's basically the number of ways I could choose 4 x's out of a total of 5. How many? And that's going to give me my x to the 4ths. How many x to the 3rds are there going to be? Well, I could choose these 3, I could choose those 3, I could choose those 3. It's basically all the different ways I could choose 3 x's out of the choice of 5. And now if I don't choose an x, it means I choose a 1. But when you multiply by 1, it doesn't do a lot. So that's 5 choose 3. How many x squares? Well, I could choose these 2 x's, those 2 x's, those 2 x's. It's all the different ways I could choose 2 x's out of 5. So it's 5 choose 2 times x squared. And how many x's? Well, how many ways can I have just 1x? So either I just choose that 1x, or I just choose that 1x, or just that 1x, or that 1x. So it's the number of ways I could choose 1x out of 5, which again is 5. We all know that. And what about the last power, the 1? Well, that's how many ways can I choose no x's out of this group of this list of 5 possible x choices. Well, there's only one way to do that. That's why I just have a 1 over here. So this again, it's just kind of a connection to the idea of choosing and the binomial theorem. And that is all I wanted to say. And yay.